Hey everybody, welcome to Fastware. Thanks for watching. So today we're going to be expanding our understanding about um, performance, and we'll be looking at the code that we looked at last time for constructors and destructors in C++, but this time we'll be looking through a different lens. We'll be looking at how to analyze the performance of your applications or your little benchmarks using perf. And I'm going to be demonstrating with this particular example because I took some liberties with conclusions saying this happened because of that reason and that happened because of that reason. And to provide more evidence for those conclusions and to demonstrate how I arrive at them, I'll be using perf to show how I collect information, so the entire process, and how do I analyze it and come to my conclusions exactly the same way. So we had this little code with the constructors, destructors, and a simple init, which just setting in a constructor some values and in destructors, so setting 1 in a constructor for 1 up to 64 integers, depending on which is it small, medium, or large or extra large. And in a destructors, we're just setting 0 to all of these integers. So we're not doing anything else. What we want to do is benchmark the cost of the call and the memory latency when the call is involved, and that code cannot be inlined, so we have to fetch things from memory. So basically trying to simulate a realistic C++ application, so to speak. So what we'll do is I have prepared a little what we have stats. So perfstats is a tool which records general statistics about your application. So I have spoken on perf before. You can find the card in the above my head. So if you haven't seen how to use perf, please look at it. Also, if you have not watched the last video, how I basically demonstrate the cost of constructors and destructors versus just simple inline code, a card above my head now as well. So go watch that before watching this. It will make a lot more sense then. So what I'm going to do is just run perfstat -d. -d is just for detailed information. And here it is. So constructor, destructors, small. And so when it finishes running, so what you will find is you have this information like context switches, CPU migrations, page faults, and blah, blah. But important information is cycles, stalled cycles for both front end and back end, instructions, branch misses, and branches executed, L1 decache misses, so this is data cache loads, and data cache load misses. And yeah, so the stalled cycles here are fairly important. So stalled front-end cycles are when instructions stall during the instruction decoding and execution pipeline. So for instance, some instructions, I don't know, are not ready yet because the previous instruction took longer to execute, or because iCache, the instruction cache, didn't put any instructions, so that pipeline stalls because there's nothing for it to do. That's recorded in the front-end cycles. And in the back-end cycles is when data is not ready. So when you're trying to execute instruction, but the data has not been loaded from memory and it's not ready yet for you to be executed. So that's what the backend cycles represent. Right, so this is fairly self-explanatory, I think. Anyway, so we ran and we collected some information, but now what we want to do is run exactly the same thing, but with this simple init, which has the inline code, and we'll try to compare the performance between those two. So here we have, let's compare cycles, around 13, 14 billion cycles for each. Okay, so stalled cycles for front end and back end are a little lower when running the inline code, but the number of instructions, because there's a lot of inline code and you don't call through a function, is a lot larger, right? So a lot number of instructions that had to be retired in order to complete our program is almost twice as large. However, that also you have a little statistic right here where you have instructions per cycle. We can see that in this kind of object-oriented model where you have the constructors and destructors, only 1.5 instructions per cycle were executed. However, the inline code managed almost 2.8 instructions, almost 3 I wanted to say, but 2.8 instructions per cycle, which is crazy. So looking at all of these, we would say, so why this simple init, which took about 25 milliseconds, and this one took about 200, nanoseconds, and this about 200, so it's about 8x performance difference. So where is that difference? Well, where do you see that difference? And I see it right here in the L1 Dcache loads. This executed almost 6 billion memory references, so asking for memory. So loading or storing, right? And here, it's only about 2 million. So it's about 2000x difference between 3000x difference between those two. And we have 8x performance difference. And it might be a little counterintuitive. You say, well, you told me, because I watched another video about caches, you said that L1 cache is virtually free. And it is. It's about 3 to 5 cycles to execute. However, with that large of a difference, 3 to 5 cycles make up quite a big number, and therefore the difference in time. So this is how I analyzed and presented information in the graphs at the end of the last video, where I said that the 8 to 9x performance difference in these very small and medium cases were due to that memory was always ready and our caches were nice and clean. That was my conclusion there. And now you can actually see the numbers right in front of you from the processor itself, what it thinks about the two different examples. And this is how I arrive at these conclusions. So now towards the latter part of that video, I also concluded that at scales where we had the constructors and destructors with very large objects in them, so these classes which had objects larger than 64 bytes, so 128 or 256 bytes, I said that these caching effects kind of disappear, and there is something else that's happening. So the function calls that starting to dominate. So the cost of the function call itself. And here, let's try to have a look. So instead of running it now small, what we're going to do is we're going to do large. So this is going to run two benchmarks, both large and large X. So for 128 byte member fields and 256 as well. So let me run this one. I'll collect some information. Here it is. Now I'm going to do exactly the same here, which we have large. Let's have a look. And we finished. Wonderful. So again, number of cycles, it's a little larger for a simple init, kind of an inline code. And we have the stalled cycles, so stalled front-end cycles, so instructions are not quite ready yet, is almost twice as large. So again, all the code is in one place and all the data is in one place. So therefore, it's just how fast the instructions can be fed into the CPU. and obviously we're constantly stalling as instructions are having difficulty catching up. So this is a problem. And also, the data are not ready constantly, right? But this is actually a bit, I would say, misleading, because all the execution happens locally, all the data and instructions are local. The faster your program can be fed to CPU, the faster it can be executed. But this is basically reaching the theoretical limits of how fast your program can be fed into the CPU. And it constantly tries to stall because it has difficulty doing that. And you can see that we have, for memory loads, we have exactly the same kind of a situation where we have 20 billion loads and here 32 billion loads. However, if you look at the time it takes to execute these, you can see that actually simple init is about twice as fast at all scales, even the largest ones, almost 3 times actually, than the constructor-destructor example. So we managed to execute many more instructions. So what is the difference between actually calling this function call and not calling a function call? We have more stalls and everything else. However, if you're calling a function call, which is a very expensive instruction, and you stall once on that, that's only counted as one. But you have here that you have, so for instance, 256 bytes, you have 8 SIMD instructions, and if it stalls on 4 of them out of 8 of them, so you register 4 stalls here. However, a number of instructions that we retire when running inline code is much greater. It's actually twice the amount of that of using function calls. And instructions per cycle also demonstrate that, with us having almost 2 instructions per cycle, while in the constructor-destructor example, only 1.2. So I think with that, maybe you found something useful here of my process, how I analyze these processes. There's also perf record. If you're interested in learning how I use perf record to, for instance, analyze these stalled cycles front end between these 2 different examples, I can maybe record that next time and demonstrate this example. But with this, thanks for watching. If you liked this video, please leave that like. Subscribe to the channel for more videos such as this, for more information. And as always, comment in the comments below. And I think my email is attached in a description. If you're having problems with any of your projects, if you don't understand why something is slow, you can send code samples. We'll analyze and I'll create a video, respond to you. So yeah, engage. Looking forward to hearing from you. Thanks for watching again. I'll see you next time. Bye.